All right, so next on the list of things to figure out is what is the most reactive. If you remember correctly, I showed you a bunch of videos. I showed you that if you go down this list over here, lithium, fizzled a little, sodium burned and exploded a little, potassium super exploded, rubidium went silly explosion, cesium was nuts, right? And you can imagine that francium, if we get enough of it to go, would be super nasty, critical awfulness. What you don't know is beryllium, magnesium, calcium, these, when they're exposed to oxygen, beryllium kind of fizzles a little bit. Magnesium, takes a lot of heat to get it started, but it'll burn pretty good. Calcium burns better. Strontium burns even better still. Barium burns better, and then it's just silly at this point, right? So it turns out there's trends also as you slide, not just they're in the same family, so they do the same sort of things, but some of them do it more. Okay? In fact, francium is the most reactive over here. Francium was the most explosive on the things that we showed you before. Okay, so let's talk about why. To start off with why, we're going to talk about two that are on the right-hand side of the graph. Let me see if I can get a red pen here. That is fluorine and oxygen. Fluorine and oxygen. So fluorine, when drawn properly, looks like this. It's got 2 electrons in the first shell. It's got 1, 2, 3, 4, 5, 6, 7. It's got this one hole it needs to put something in. Oxygen, on the other hand, has 2 electrons. 1, 2, 3, 4, 5, 6. Remember, the electrons don't like each other, so they're spread out. So it's got one hole over here and typically one hole over here. So which one is more likely to get excited? Which one's more likely to react violently when exposed to another chemical? And the answer to the question is fluorine. Why? Two reasons. First of all, and this is the least significant of the two, fluorine has 7 protons. Fluorine has 9 protons. And oxygen has in the middle of it only 8 protons, which means this thing likes to pull the negative electrons in more. It wants more negative electrons than this thing. That's one reason. Second reason is this. There's only one hole to fill. So this fluorine will react with anything. All it wants to do is steal one electron. In fact, if it can steal it from anything, it is the strongest stealer there is, right? It just one electron makes it happy, very close to nucleus, so you're going to be really close, a bunch of positives. Come on in, visit this electron, you're good to go. Oxygen has 2, they're usually on opposite sides, so even if I want to donate 2 electrons, one's got to go here, one's got to go here, it's harder to do. Okay? And so oxygen is less reactive than fluorine. And in fact, if you go down the chart, nitrogen's less than oxygen for the same reason. It takes 3 to make nitrogen happy. It's hard to react when you need 3. Okay, so nitrogen's less reactive than oxygen, and fluorine's the most reactive of that set. Okay, same thing, by the way, happens down here. Okay, this is a better one I'm more familiar with. Okay, tellurium hardly reacts at all. This is basically inert, doesn't react with almost anything. Tin we make cans out of because it doesn't do anything. Gets stronger and stronger and stronger. Iodine, yeah, you put iodine in something, you can kill it. Okay, so we used to use iodine in backpacking trips, because you'd scoop up some water, you didn't want any bacteria, you'd throw some iodine crystals in there and it'd kill the bacteria. Not really great for you. That's why probably nowadays they don't let you do that. All right, let's go question number 2. Question 2 is lithium has one extra electron, so let's go back to lithium. Lithium has 3 protons, has 2 electrons in its first shell, whizzing around, and it's got one way the heck out here. And then the next one over, they're talking about beryllium. Well, beryllium has 4 protons. So it's got a stronger positive. It's got 2 electrons. And it's got 2 more way the heck out here. So lithium wants to lose its 1 electron. It's in the outer shell. Beryllium wants to lose a 2 in the outer shell. which makes perfect sense. Which one's more reactive? Well, it's much easier to lose one than it is to lose two, right? Especially considering they'd be on opposite sides of the atom. So therefore, it's much easier to lose one than two. So therefore, lithium is more likely to react because it all it has to do is find something with one electron and it's happy. Okay? Beryllium has to go to the trouble of figuring out how to dump two to be happy. Even more so, if you look at the nucleus is 4 protons versus 3 protons. Now I'm trying to get rid of an electron. Electrons like protons, right? So this one that has 4 protons is more attractive than this one likes 3 protons. So what happens is lithium is more reactive than beryllium. And it turns out as you go this way on the chart, they get more reactive this way. All right? Which makes sense, right? Aluminum is not very reactive. You saw sodium. Like sodium you saw put with a little bit of water, it explodes. Magnesium, which is the next one over. Let me see if I get my pen in the right spot. Magnesium, which is the next one over. And magnesium was used in World War II in bombs. We were firebombing countries that we were fighting with. And when we did so, we dropped some magnesium in there. Why? Because hot magnesium mixed with water, the magnesium would strip the oxygen out of the water, right? And catch on fire. And so people pouring water on their fires, this would cause it to get hot and reburn. So you couldn't put out the fire with water. You actually were feeding it with water. Okay, so it wouldn't work. Okay, so that's not as strong as sodium, which just explodes when you put in water. But magnesium, if hot, does something similar. Aluminum, you put water on aluminum in explosions? No. Silicon and water ignore each other altogether. Okay, so as you go this way, it gets stronger. The reactions get stronger. So as you go to the two extremes of the chart, the reactions, they can become more reactive. The exception to that rule, of course, is this row right here. Remember this column right here? That's noble gases. They don't react with anything. So they're the least reactive by far because they're already happy. They're good. They got it all. All right, let's talk about fluorine. Fluorine is smaller than, so fluorine has, again, 9 protons. It's got 1 set of electrons on the inside. Another 1, 2, 3, 4, 5, 6, 7, and 1 hole. And then chlorine, which has 1, 2, it has a whole lot more protons, so it's got 15 protons. 15 protons. It's got 1, 2 electrons out here. Then it's got another layer of electrons here, full. There's 8 of them in here, right? 8, 8, 8, 8, 8. And then the next one all the way out here, way the heck out here, big time farther bigger, right? Has got another 7 in it. 1, 2, 3, 4, 5, 6, 7. So each one of these has a hole. So they're both fairly reactive because they both want to fill up this one spot where they've got an electron missing. Which is stronger and why? Well, the answer to the question involves the fact that if you look at the nucleus here, it's much closer to the hole than this nucleus here is to that hole. These are the positive charges. That's what draws your electrons in, right? If it's much farther away, it's much weaker, whereas this is much, much stronger. So the smaller the atom, when you're trying to suck in electrons, the closer it is to the protons, which makes it excited and want to come in. So atoms become more reactive as they go this way. And in fact, the most reactive one on this side of the chart is fluorine. Okay? Fluorine is the most reactive on the chart. So the closer you are to fluorine, the stronger you are. Okay? They get more reactive as they slide on this side of the chart. Hold on. On the grabbing electron side, they're more stronger the closer they are to fluorine. The more they're this way, the more they're this way, the stronger they are. All right. What about cesium? Well, you figure the reverse is going to happen over there. Why? Because cesium and francium. I'm not going to draw all the different shells, but you can imagine we've got a big old nucleus. And we got layer upon layer upon layer of electrons. We got an electron out here. That's cesium. Francium, layer upon layer upon layer upon layer. And it's an electron that it's trying to hold on to is way the heck out here. Actually, it's trying to get rid of right out there. So this has got one more layer. Cesium would fit like inside. It'd have one less layer. So this one electron is even farther away from the protons. Remember, that's what's attracting it. What's holding on is those protons. The farther it gets away, the easier it is for it to dump this one electron. Okay, so the more shells, the stronger stronger these elements are for getting rid of electrons. So if your goal is to get rid of electrons, you want to be bigger. If your goal is to attract electrons, you want to be smaller. So they get stronger as they go this way. And so the simplest way to look at it is the more like francium or fluorine you are, the stronger the reaction is. All right? Fluorine and francium are the two strongest elements. They suck paint off, right? They're ready to donate. This one's going to donate electrons to anything that goes by. This thing wants to suck down electrons no matter what. Okay? So all you have to do is compare the two and say which one's closer to fluorine. So let's take a look. Which one's more reactive, F or S? So I look over here. Here's F. Here's S. Which one's more like fluorine? Well, fluorine is. Okay, it's a bad example. Let me see if I can get you a better example. Let's see if I can pop up a better example. Let's go iodine or tellurium. Okay, so iodine or tellurium. So here's iodine. Boom. Here's tellurium. Which one is closer to fluorine? Well, tellurium wants to get to fluorine, right? Tellurium is farther away because iodine's in the same column, right? So therefore, which one's stronger? Iodine's stronger. Okay? The more you go this way and the more you go up, the stronger you are. The more you go this way, the more you go this way and the more you go down, the stronger you are on this side of the chart. Okay? All right, try to finish out this worksheet. It shouldn't take you too long. If you have questions, send them to me, and I will try to answer them.